Welcome to video 4, the second last video looking at the trial exam solutions. Picking up with question 29, we have a feature wall consisting of a rectangle and a semicircle which is being built with the dimensions as shown. We want to calculate the area of the wall correct to the nearest square metre. Now we've got two sections there, a rectangle and a semicircle, so let's just put in a yellow line there that splits them into the two. So now we can clearly see what our two areas are. Let's call area 1 our rectangle and area 2 our semicircle. So let's look at the area of a rectangle. Well, hopefully we remember that that's just length times width. Our measurements are given to us, 3 metres and 2.5 metres. We just want to multiply those two together to get an area of 7.5 metres squared. Area 2 is a semicircle, so that's half a circle. Area of a circle, pi r squared, so we want half of pi r squared. So what's our radius? Well, we know that the full width across our semicircle is going to be 3 metres, so therefore our radius must be half of that, 1.5 metres. So we can put in 1.5, type all of that into our calculator, and we get that area 2 is 5.534 metres squared. So that's area 1 and area 2. I want the total area of the wall, so I'm going to add those two areas together, and that gives us a total area of 11 square metres. Part B, we want to use two applications of the trapezoidal rule to calculate the approximate area of the wall, giving our answer to two decimal places. So what we need to do now is split that wall rather than into a rectangle and a semicircle. We're going to split it in half down the middle because it says we want to use two applications of the trapezoidal rule. So we've got two trapeziums there. We're going to have an area on the left-hand side and an area on the right-hand side. Now from our summary sheet or our reference sheet, we get that our trapezium or trapezoidal rule is going to be h over 2 multiplied by df plus dl. So what we're saying is that df and dl is going to be the first and the last sections of our trapezium, and h is the height or the distance between df and dl. So if we look at our diagram, what we've got there is df on the left and dl will be our yellow line. H is the distance between the two. Now we knew that the full distance across the wall was 3 metres, so h is going to be half of that, 1.5. Well, df, we know that that's going to be 2.5, but what about dl? Well, that's going to be our 2.5 plus the radius of our circle. And we knew that our radius is 1.5, so that means that dl, the total height will be 2.5 plus our 1.5, so that's going to give us 4. So substituting all of those values into our equation, an approximate area on the left is going to be 1.5 over 2, multiplied by 2.5 plus 4. So we're adding the first part, df, 2.5, plus the second part, dl, of 4, to work out what's the average height of that section. Right? We divide that by 2 to get our average height, and then multiply it by 1.5 to get an approximation for the area on the left-hand side is going to be 4.875 square metres. What do we know about the area of the right? Well, the area of the right is going to be exactly the same as area on the left, right? Because we've nicely split it in half. It's a nice symmetrical shape. It won't always work that way, and sometimes we're going to have to then work out a separate area. In this instance, they're exactly the same, so the area on the right is also going to be 4.875. So what's our approximate area of the total wall? Well, we're going to have the area on the left plus the area on the right, which is two lots of our 4.875, which means the approximation of the wall is 9.75 metres squared. Now in part A, we worked out the exact area was 11 square metres. Part B, the approximation is 9.75 square metres. So obviously we've underestimated. So now in part C, we want to show that we underestimated it by approximately 11.4%. Well, we know from part A the area of the wall was in fact 11 square metres. Part B we approximated at 9.75 metres, so now we want to work out is that roughly underestimated by 11.4%. How do we do that? Percentage change that you would have learned way back in year 8. It's the difference between our two values times 100 because we want a percentage, and then we're going to divide that by what was the actual area that we've had. So in this instance, the difference is 11 minus 9.75 times 100 divided by 11. You can type that straight into your calculator. Otherwise, 11 minus 9.75 is 1.25. Regardless of which of those two lines you type into your calculator, you're going to get 11.36. 11.36, if we round that to one decimal point, that's 11.4%. So there you go, we have shown that yes, our trapezoidal rule did underestimate the area by approximately 11.4%. Question 30. The emergency stopping distance, S, which is measured in meters, that is required by a motorist on dry surfaces, so this is how far it takes us to actually stop. It consists of two parts. The first part is the reaction distance R, which is how long it takes us to react to needing to stop, plus the braking distance B, which is how long it takes the car to actually come to a stop. Both of those are in meters and is given by the following formulas. R is equal to 0.7 times V, B is equal to 0.01 times V squared, and S is equal to R plus B, where V is the speed of the vehicle in kilometers per hour. So we want to show that when a motorist is traveling at 70 kilometers per hour on a dry surface, the braking distance and the reaction distance are going to be equal. Now there's a couple of ways that we can work this one out. Well, first thing we know is that R is 0.7 V, that's given to us. So we know that it says when we're traveling at 70 kilometers per hour. So if we substitute in V is equal to 70, so then what's going to happen is that we get 0.7 times 70, and that's 49 meters. The other thing that we know is that our B, our braking distance, is equal to 0.01 times V squared. Again, we've got V of 70, we substitute that in, and then that equals 49 meters as well. So therefore, when V is 70 kilometers per hour, our reaction distance and our braking distance are equal. Part B then says, what is the stopping distance when traveling at 70 kilometers per hour? Well, our stopping distance S is equal to R plus B. So both R and B are 49, so we're going to add 49 and 49 together so that we get a stopping distance of 98 meters. So part C now says, on this diagram, we have the graph of the braking distance. And what it wants us to do is draw the graph of the reaction distance from a zero velocity up to a velocity of 100 kilometers per hour. So what we need to do then is pick those two particular points. So the thing we are graphing is reaction distance, so that's our R equals 0.7 times V. So the 2 points it wants us to graph to and from are 0 and 100. So let's plug those particular values in. So let's start with V is equal to 0. 0.7 times 0 is going to be 0, so that gives us the 0.00. There it is down there. The next point is 100. So when V is 100, we get 0.7 times 100, which is 70. So we come across on our x-axis to 100, we go up to 70, and we put in a second dot. Now, we could have picked any two dots because it's a nice linear line. It won't make any difference which points we pick, but it says to go from 0 to 100, so let's pick those two particular values. So now we can draw ourselves a nice straight line that connects up those 2 points, and that there is our graph. Part D, if 0.01 V squared equals 25, what is the value of S? So our 0.01 V squared, if we look at our formulas, we see that that's B. B equals 0.01 V squared. So if 0.01 V squared equals 25, we can therefore say that B is 25. Now, if we go and write out our equation that we had, that's 0.01 V squared equals 25, I'm going to see what our value of V is going to be. How can I get out a value of V? Well, if I divide both sides by 0.01, we're going to be left with V squared on the left. 25 divided by 0.01 is 2,500. So if that's velocity squared, if I take the square root of both sides, square root of V squared is just going to be V, and the square root of 2,500 is going to give me 50. So therefore, our velocity in this situation is 50 kilometers per hour. Now, we already worked out what B is. Our ultimate question is, what is S? Well, S is equal to R plus B. If we've got B, we now need to find out what R is. So R is 0.7 times the velocity, and we just worked out that our velocity is 50. So 0.7 times 50 gives us a R value, our reaction distance, of 35 meters. So now we can go ahead and find out our S, because that's equal to R plus B. R we just worked out was 35, and it told us that B was 25. So when I add the two of those together, we get a stopping distance of 60 meters. Question 31. A diagram shows a vertical pole PQ and a building RT both standing on level ground. Because they're standing on level ground, that means that they're going to be, we assume, built properly and have a 90-degree angle. Now, both of those have nicely been put in on the diagram. The pole is 90 degrees to the ground and the building is at 90 degrees to the ground. Now, from the top of the pole, the angle of depression of the top of the building is 32 degrees, and then the angle of depression to the base of the building is 68 degrees. On a direct line of sight from the top of the pole to the base of the building, the distance is 55 meters. Mark that given information on the diagram and then explain why angle PRT is 122 degrees. Now, it says that we are talking about angle of depression from the top of the pole. When we talk about depression, it's measuring down from the horizontal. So I'm going to put in a horizontal line. All right, that's running parallel to QT. Now, it says that the angle of depression to the top of the building is 32 degrees. So coming down from that horizontal line to the line PR to the top of the building is 32 degrees. Coming down to the base of the building, so this is coming down to the line PT, that's going to be on an angle of 68 degrees. Now, the third piece of information we've got there is that the distance from the top of the pole to the base of the building, so the line length there, PT, is going to be 55 meters. Now, what other information can we find out? Because that's all that we've been given. Well, we know that our 68 degrees down from the horizontal to that line with the 55 meters is going to be the same as coming up from the ground to that same line, PT, that green angle. Right? Because our horizontal line that we drew in is running parallel to the bottom there, that orange angle, 68 degrees coming down, and the green angle coming up are alternate angles. So they're going to be the same size. So then we can say that the green angle is also 68 degrees. How is that helpful? Well, we know that that's 68 degrees, and then the angle from that line to the building, that blue angle there, the green angle and the blue angle make up a 90-degree angle. Well, if that's the case, the blue angle must therefore be 90 degrees minus 68 degrees. So the blue angle must be 22 degrees. Now, the other angle that we can find is that dark red angle in there, because that's the difference between 68 degrees and 32 degrees. So if we do 68 minus 32, we get that the dark red angle is 36 degrees. So now we know that that particular triangle PRT or TPR or PTR, doesn't matter what we call it, the three angles in there must add up to 180 degrees. So therefore, angle PRT is going to be 180 degrees minus the two angles that we have, 36 degrees in the dark red and 22 degrees in the light blue. So if I do that in my calculator, what we're going to do is add 36 and 22 together to get 58. 180 minus 58 leaves me with 122 degrees. Right, so we've explained why that angle, PRT, is 122 degrees. Right, if we had to use any, if we had to state a specific rule, it would be because there are 180 degrees in a triangle. All of the information that we've got there shows the working of how we got there. That would be sufficient. So part B, use the sine rule to calculate the height of the building RT correct to the nearest meter. Now, let's say we didn't know how to do part A. It doesn't matter because we've got that 122 degrees was given to us. So we can write that straight in. Right? I've already put it in there on the diagram, but we could write that in and skip part A and then go on to part B. Because part B is using the sine rule. And we want to find the height RT. Well, the 55 meters was given to us. That 122 degrees was also given to us. So the only piece of information that we kind of need is one of the other angles. So hopefully we can, just by looking at the angles given to us, 68 and 32, we can find the difference in the middle there is 36. So remembering that our sine rule is A on sine A being equal to B on sine B, we're going to have A, the length we want to find, be RT. So then that's going to be over our angle RPT, which we know is 36 degrees. That's the difference. And then that's going to be equal to B, the length given to us, 55 meters, I should say, over the angle that was given to us, sine of 122 degrees. Right, so even if we didn't know how to do part A, we've been given that information. So now I want to rearrange that to get RT by itself. So I'm going to multiply both sides by the sine of 36 degrees. And now if I put all of that into our calculator, it tells me that the length RT must be 38 meters. All right, so that's the height of our building, 38 meters. Part C then is how much taller is the pole than the building? Well, what we're going to need to work out is what is the height of our pole. So if we look at our pole there, it makes a nice 90-degree angle with the ground, and then we've got that 68 degrees coming up from the ground. So what we've got then is the hypotenuse of that triangle is 55 meters, and we've got an angle of 68. So we can just use one of our trig ratios. So if we call that 68 degrees theta, there's our hypotenuse there across from our 90 degrees. Across from our theta is our opposite, and that's what we want to find. Doesn't matter about the adjacent, we could write that in there if we wanted to, but we've got our hypotenuse, we want to find our opposite. So which one of the three trig ratios uses opposite and hype? Well, that's going to be sine from SOHCAHTOA, so therefore sine of theta is opposite over hypotenuse. Theta we know is 68 degrees, our hypotenuse we know is 55, and the opposite is what we want to find, which is PQ. Multiplying both sides by 55, so PQ is equal to 55 times the sine of 68, and throwing that into a calculator, we get that the height of the pole PQ is 51 meters. That's not what the question wants us to find though. We want to know how much taller is the pole than the building. So we want to know what's the difference between our 51 meter high pole and our 38 meter high building. So the difference is 51 minus 38. That's a difference of 13 meters. All right, so the question is how much taller is the pole than the building? The pole is 13 meters taller than the building. Question 32. The scatter plot below shows the number of calories burned during exercise over time with a line of best fit drawn in for the recorded data. Describe the correlation that exists in this data. So the correlation is how close is that line of best fit to the dots that we have. Well, if we look at that, we can see that the dots are pretty close to that line, so we can say that it must be a strong correlation because that line is pretty close. That'll only give us half a mark though. The other piece of information we need to make comment on is this positive or is this negative? Well, as our exercise increases, the calories burned also increases, so therefore it must be positive. So we would describe it by saying it was a strong positive correlation. We could also say it was linear. It doesn't really matter. Part B then says explain why the value of the Pearson's correlation coefficient would be greater than 0.9. Well, remember that our values for our correlation coefficient are going to be between -1 and +1. Right? All our values of R must be between -1 and +1. Well, we know that this is a nice positive correlation because we've said that already, right? It's a positive gradient, so R is going to be positive. And again, the closer those dots are to the line, the closer it's going to be to 1. If they were perfect on that line, it would be 1. It's not quite perfect, but it's pretty close. So because they're almost at that point 1, we can at 1 rather, we can say that it is 0.9. All right, must be greater than that. All right, so it's very similar to what part A was asking. It's just looking at it at a slightly different thing, which is just explaining it a bit better. Part C then says write down a suitable equation for that line of best fit. So remembering that our line of best fit is going to be in the format of y hat equals mx plus b. M is our gradient of the line and b is our intercept, our y-intercept of that line. So we're going to have to bring that line back to work out where our y-intercept would be. And that looks like it's going to cross at the point 0, 0. So therefore we can say that our b is going to be 0 and it's going to disappear. So our line must be of some sort of format of y equals mx, right? B is 0, so we don't have to worry about it. M is our gradient. How do we find gradient again? Well, our gradient is just rise over run. So we need to pick 2 points and then work out what is the rise between those 2 points and what is the run between those 2 points. Now, this is when we talk about 2 points, we're talking 2 points on our line. Okay, this is not the points given to us, but the points on the line. So I can pick any points we want. Well, I'm going to pick the point 0, 0, where it touches the y-axis that we just worked out. And then I'm going to pick the point 100, because I can easily read that off. But I could have picked any 2 points. I could have picked the point 550 and then the point 10, 100, or I could have picked the point 550 and the point 40, and then where does that look like it's going to be crossing? Right, it's a little bit below 400, so I can't pick 400. So I could estimate 390, 380. As soon as we start doing that, though, it gets less accurate. So I'm going to pick 2 points that I can easily read off that graph, either 0, 0 or 550, and then the point 10, 100 would be acceptable. Anything to the right of that is going to start getting difficult. So what's the rise? How far have we gone from 0 up to 100? Well, that's going to be 100. What's my run? How far have I gone from 0 to 10? Well, that's just going to be 10. So there's my rise over run, 100 over 10. So that means my gradient must be 10. Now, if I picked a different point, like I said, we could have picked the point 550. What's my rise there? Well, that's going to be 50. What's my run? 5. 50 over 5 also gives me 10. So either way, that would be acceptable. So what that means, my gradient m of 10, I can put that into my y hat. To get that y hat is going to be equal to 10x. Part D then is comment on whether the line of best fit could be used to estimate the calories burned while exercising for more than 45 minutes. Now, the last data point we have there is for 45. Can we accurately predict then for time greater than 45 minutes? So we have to remember 2 pieces of important information. What we are doing is we are going beyond the scope of the given data, so that's called extrapolation. Is it safe to extrapolate? Generally, no. The further we are away from the data, the more risk we have with extrapolation, because anything could happen. Think about exercising for more than 45 minutes. Can I say then that line's going to keep continuing like that? What about if we exercise straight for 2 hours? One would assume we're going to start getting tired and exhausted, and we're going to be burning less and less calories. So that straight line is going to start curving down. So the more that we try and go beyond that 45, the less reliable our extrapolation is going to be. So what we can therefore say is that because this correlation is pretty strong, all right, it's a nice, good, strong linear relationship, for a little bit beyond 45, it will be safe. All right, so since the correlation is a strong linear relationship, we can estimate the calories burned beyond 45 minutes, so long as we do not extrapolate too far beyond those 45 minutes. So we could use this for 50 minutes, 55 minutes, maybe an hour, but anything beyond that, there are too many confounding variables that will affect our results. So like I was saying before, we start getting exhausted. There's obviously going to be a maximum number of calories that we can burn off. All right, so think about how many calories we could possibly be burning off. We're going to reach a point where the amount of exercise we're doing, we can't burn off more calories than we have to burn. So that's going to be one of those confounding variables. Likewise, how exhausted we get. Let's assume we're exercising in a gym. That gym might shut, so there's another confounding variable. We don't have to identify what they are. We just have to be aware that there will be confounding variables that will affect how accurate this particular prediction line is. And that brings us to the end of this video. We have one more video left to do, which will complete the solutions for this exam.